Well, hi, welcome to our lecture on packet 22. We're focusing in this packet on section 3.9 in our calculus textbook. We're going to be talking about derivatives of general, exponential, and logarithmic functions. Our two main goals are these two. We're going to do the derivative formula for b to the f of x, and we're going to go and find the derivative formula for log base b of f of x. And along the way, we're going to discover the rules for a couple of other related functions. In particular, we're going to find what the derivative for b to the x is, and also what the derivative for the natural log of x is, as well as the log base b of x. But our true goal is that we want to be able to take the derivative of anything, right? And so, our goal is these most general forms, b to the f and log base b of f of x. This builds heavily on the use of the chain rule, and in a couple of places we're going to use implicit differentiation in order to do that. So prerequisites for this are the chain rule and a bit of implicit differentiation. Although we aren't going to find any slopes of tangent lines to implicit curves, we're still going to use the principle of implicit differentiation. Let's start by reminding ourselves of this fact here, that the derivative of e to the x is e to the x. But we really want to be able to put something more general in place of this x right here. I don't want to restrict myself just to plain old x's, and I really don't want to restrict myself to just e. What's so special about Euler's number e? Anyways, the derivative formula, so this is stepping toward the fully general one, is I still have base e in this formula for the exponential, but the thing that's changed here is that I have any function, any differentiable function f, and we have the rule for it. When you take the derivative of e to the f of x, you have e to the f of x, and then there's the action of chaining out that hopefully is starting to become really familiar right here. So we've got the f of x is inside, and we're going to chain out the derivative of the thing that's inside when we take the derivative of e to the f of x. I mean, it doesn't matter whether that thing is called f. It could be called u or phi or whatever you want. Generally, it's actually not going to be named. But I have to have a name for it in order to be able to put something in this box. So let's do an example of how this works. I've got e to the, and I've got stuff inside here, right? So our inside function is x squared plus 2x plus 1. And so if I were to call that, say, f, we should never get attached to our actual function names, then f is like e to the u, where u is equal to x squared plus 2x plus 1. And so I kind of have like f of u, and I have u of x if I want to make their variable dependence completely explicit. So I can compute df du, that's e to the u, and du dx is equal to 2x plus 2. Then the chain rule tells me that df dx is equal to df du times du dx. And so I'm going to take these pieces that I found and put them together. And I get that df dx is equal to that product, which is equal to e to the x squared plus 2x plus 1 times 2x plus 2. So let's match that up with the formula that we had above. Well, I have e to the f of x, okay? So like e to the a thing inside. The result, the derivative, here's the derivative of this expression. I've got e to the f of x, fine, e to the f of x, and on the outside, f prime of x, or the derivative of the inside thing. Doesn't matter what we call that inside thing. So this next one here, I mean, these problems are basically perfectly analogous. So this next one over here, if I call that, say, equal to f, then df dx, we're going to recognize that I've got not just x, but something more complicated on the inside. And so df dx is equal to e to the sine x, and then chain it out, cosine x. I think I'm going to erase that arrow, and I want that to be in a different color. Okay. This 2 to the x looks like it's a little bit different from the previous ones, and I so far only know that dx of e to the f of x is equal to e to the f of x times f prime of x, and I've got e, not 2, and here I have 2, not e. But that's okay, because I can use a rule that 2 to the x is equal to e to the natural log of 2 times x. So what I'm going to do is I'm going to rewrite this function. How about I call this g? So g equals 2 to the x is also equal to e to the natural log of 2 times x. And it's not natural log of 2 times x, it's natural log of 2 times x. So g prime is equal to e to the natural log of 2 times x times natural log of 2. Now, we do often like to put these, so that I don't accidentally like take natural log of 2 times x. I'm going to take that x and I'm actually going to put it in front. I'm going to take that and actually put it in front. So I'm going to rewrite g prime equivalently as natural log of 2 times e to the natural log of 2, or x times natural log of 2. Another simplification that we could make, if I don't like that, is we could recognize, oh, well, that's just the number 2. And so I could write that g prime is equal to natural log of 2 times 2 to the x. Let's do one more example. Let's do this one right here. Let me call that, let's say h. I've got a thing inside. It's not just x. I've got a product. So we're going to use the product rule on that one. So when I write down what h prime is, go ahead and pause the video and give that a try. And then come back when you're ready to see me work through it. All right, let's go ahead. The derivative of e to the is e to the. So I'll have e to the x times sine of x, and then chain it out as usual, times, I'll put it in parentheses since I've got to product it, 1 times sine of x plus x times cosine of x. And if you don't really like that 1, we could go ahead and take it out. So I feel like the e to the problems are pretty straightforward. Just do a little bit of grind to develop the skill, and I think that you'll find these pretty straightforward too. Let's turn the page. So I want to show you, work through with you the next level of generalization that we want. So d dx of b to the x for some base. What happens when I get that? Well, I pick up this factor of natural log of b out front times b to the x. Okay. What's cool about that one is that if my base is equal to e, then I have that b to the x prime equals e to the x prime, but that's just equal to the natural log of e times e to the x, and this is the fancy number 1. Natural log of e is 1, which is just e to the x, and so we recover as a special case e to the x prime equals e to the x. This is a special case of the general rule that b to the x prime is equal to natural log of b times b to the x. So you just pick up, the only thing that's different here is that you pick up this prefactor of natural log of b if you have something other than e, and it's always been there hiding. It's just 1 in the case that the base is the special number e. Okay. The most general exponential rule is this one right here. So this one builds off of the one where I have base b. The only thing that's different here is that I have this f of x upstairs instead of just plain x. And what happens is, well, we chain it out. So let's derive the formula. The derivative of b to the x is natural log of b times b to the x. And sometimes we just did this on the previous page. So I'm going to flip back to the previous page. Go ahead and look back in your notes. We kind of did this when we did the derivative of 2 to the x. And we found natural log of 2 to the x. So the only thing that's going to be different is that I'm going to, instead of having a 2, I'm going to have it in general with a b as a parameter. So what I'm going to do in order to derive this is I'm going to rewrite f of x using the fact that b is equal to e to the natural log of b. Because x and natural log are inverse operations of each other. Okay, so we're going to rewrite this, and I have e to the natural log of b times x. Again, reinforcing the fact that this right here is just a number, and this is not in the natural log. So when I take the derivative, I'll have f prime that's equal to b to the x prime is equal to, well, the derivative of e to the is e to the, so this is equal to e to the natural log of b times x. And then I've got to chain it out, right? We're going to chain it out, natural log of b. And then we'll realize, oh, that's just b. And so I write this as b to the x times natural log of b. And then we really like for our scaling coefficients to come out front in a lot of cases. And so this is natural log of b times b to the x. Okay. So let's do some examples of those things using the formulas that we now have. So I've got f of x is e to the x. F prime of x is equal to e to the x. G of x is e to the 3x. That means that g prime of x is equal to e to the 3x times 3. And we really like to write that 3 out front. And so we'd actually generally write that as 3e to the 3x. So that 3 is the same as that 3. If h of x is 4 to the x, then h prime of x is equal to natural log of 4 times 4 to the x. Right? Because this part right here is natural log of b, where that 4 is the base b. Let's combine them together and do this derivative of this function k of x. This looks like b to the f of x. Go ahead and pause the video, refer up to the formula up top, and try to do this derivative. And then push play when you're ready for to work it with me. Okay, so let's revisit what I do. I have b to the f of x. I pick up the prefactor because I have b as my base, so I pick up this prefactor. B to the f of x stays the same as b to the f of x. And then I chain out the derivative of the inside thing. So then k prime as a function of x is natural log of 4 times 4 to the 3x times 3, where this 3 right here is the derivative of that. And this part right here, well, 4, this is natural log of b, and 4 is my base b. You can write that as 3 times natural log of 4 times 4 to the 3x, specifically leaving space right here so that I don't interpret it as natural log of like 44 to the 3x or something like that. Yeah, there are all these like little things, little niceties that we do to make our functions easier to not make mistakes with. Okay, so that's the general exponential rule. Let's go ahead and turn the page and work on something new. So let's work on derivatives of natural logarithmic functions. I've got natural log of x. It's going to take the derivative of natural log. I get 1 over x. This one's really cool, or x to the minus 1. And in general, if I have something other than just plain vanilla x in my function, we chain it out. So I'll have my 1 over something. So here's my 1 over something times the derivative of the inside. We've got to chain it out. And then sometimes we like to move that as a way of writing it maybe simpler. And it's the ratio of u prime over u. So I think I'd like to derive this, and then I'll make a quick note about how I think this is really cool. So let's derive this. So let's start with the statement that f of x is equal to natural log of x, and we're deriving the formula. So I think that what we should do, because I kind of don't know how to deal with this, supposing I don't already know the formula, let's go ahead and exponentiate both sides. Because that's going to turn my log into something I can deal with. So let's take e to the f of x. It's equal to e to the natural log of x. this part right here, that's just equal to x. Because x been natural log or inverse operations of each other. Which means that I have, kind of wish I'd written in purple, that I have e to the f of x is equal to x. So now let's take the derivative. So now let's take the derivative. And that means that I have e to the f of x times f prime of x is equal to 1. Now I want to get f prime by itself. So let's solve for that. And what we'll find is that, so let's divide by e to the f of x on both sides. So then I have f prime is equal to 1 over e to the f of x. But f of x is equal to natural log of x. So we'll substitute that in. So this is equal to 1 over e to the natural log of x, and e to the natural log of x is just x, so this is equal to 1 over x. Cool. I think that's a really cool technique to, as kind of a circular way to get around this. Is to kind of like, okay, well, I don't know, so we'll just exponentiate both sides and get rid of the natural log, which I didn't know how to deal with, and replace it with the exponential that I do know how to deal with. And then work some stuff, substitute away, and then eventually I get the thing that I wanted. So in general, if I have a function g, which is a natural log of something on the inside, so I've got composition going on right here. I've got some inside function. When I take the derivative of it, I'm going to go g prime of x is equal to, well, the derivative of natural log is 1 over. This is equal to 1 over u of x. And then we're going to chain out the derivative of the inside. Okay. So one thing that I think is really cool is that this is kind of an aside, and then we'll do some practice problems with these. That like if I take the derivative of x to the 0 prime, so x to 0 prime, that's equal to like 1 prime, which is 0. Okay. X to the 1 prime is equal to 1. X squared prime is equal to 2x. X cubed prime is equal to 3x squared. So let me put an x to the 0 right here. And then let's do x to the minus 1 prime. I get minus 1 x to the minus 2. Let's do one more. X to the minus 2 prime. That's minus 2 x to the minus 3. So, like, what's up with the missing minus 1 that's right here, right? Because we've got minus 3, minus 2, should be minus 1, 0, 1, 2. Well, we can't possibly get there from a constant function. So, where does x to the minus 1 come from as a derivative? And the answer is the natural log function. So it's just like, it's so weird to me that natural log of x prime is equal to x to the minus 1. And like, here it is. Here's the missing minus 1. We found it. It comes from the natural log function. And I just, that is like that's so weird that like all of the powers work, and this works for non-integral powers too. All of the powers work for the power rule, except for this one case, right? And you pick up the missing case from natural log. That is just like, wow, that is so cool. Wow. Okay, let's do a couple of examples. Let's take the natural log of the sine of x. So I've got a thing on the inside here. So u of x is equal to sine of x. So f prime of x is equal to, the derivative of natural log is 1 over, oops. Got a little ahead of myself. 1 over, leave the bottom part alone, and then multiply by the derivative of the inside. Okay, weird. So that's where I get tangent from as a derivative. Okay. Let's do this one here. So I'm going to approach this problem. Let's get g prime of x. At the top level, the thing that I have going on is this to the fourth. And so I need to deal with that to the fourth with a power rule. Let's do that power rule first. So 4, leave them inside alone. And now we'll chain it out. Times, now I've got the derivative of natural log. Let me go ahead and put what we're going to have natural log of x squared plus x prime. So 4 natural log of x squared plus x cubed times, now let's go ahead and do that prime on this natural log. Let's see here, I put the thing that's inside on the bottom, and then I take its derivative and put it on top. And I don't see any other available simplification, and so I'm calling that one done. I would definitely recommend trying plenty of problems in the book to get your hands on this techniques. Let's turn the page. So all of that previous stuff was log base e, and I want to focus on log base b. I don't want to restrict myself just to Euler's number. I want any number that I want right there. So this is really similar to the formula for e to the x, or b to the x, the derivative of b to the x. So the derivative of log base b of x, I pick up this prefactor right here of 1 over natural log of b. And then we can mush them together, the two terms in the product. So this is really similar to b to the x prime. I have natural log of b to the x. And I pick up this prefactor. Log base b of x prime is equal to 1 over natural log of b times 1 over x. So they both pick up a prefactor. When it's log, it's 1 over. When it's log, it's 1 over, and when it's x, it's not 1 over. And in general, if I want to put, I meant to have this be log base b. That's okay. We can write it down what it should be anyways. So dx of log base b of u of x is equal to, it's going to be this same expression, except I pick up a 1 over natural log of b times u prime over u. Right? The only way that that differs is that I've got this prefactor of the 1 over natural log in front. Sorry, I missed that. Let's copy paste now. So we can derive this pretty straightforwardly. It's going to be really analogous to what we did for the natural log. So I'm going to start by rewriting this expression. So we're working on this here. So I'm going to rewrite this by taking b to the of both sides. So b to the f of x is equal to b to the log base b of x. But the right-hand side, b to the log base b, is just equal to I lost my train of thought. Give me a second to think. Let me think ahead on what we're going to do here. So the next thing we're going to do is we're going to take b to the f of x prime, and that's going to be equal to the right-hand side prime. And on the left-hand side, I'm going to pick up natural log of b times b to the f of x times f of x prime, or f prime of x. And on the right-hand side, I'm going to have this is equal to, I really want this to be, 1, I think. So I think that's supposed to be x. Yeah, yeah, that's right. Yeah, that's right, because b to the and log base b are inverse operations of each other. Yeah. That is to say, yeah, that b to the log base b of x is equal to just plain x. Yeah, so okay, so cool. Okay, so I have x right here. Then when I take its derivative, I pick up the 1 right there. And now I'm going to solve for f prime of x and do the substitution. So this means that f prime of x is going to be equal to 1 over natural log of b times 1 over b to the f of x. And now just like we did when we derived natural log, now I'm going to sub back in here. So that's equal to, that's equal to 1 over natural log of b times 1 over b to the log base b of x. And this whole thing, nope, there's an f of x right there. And this thing right here is equal to f of x. Yeah. So that's equal to 1 over natural log of b times 1 over f of x. I feel like... Oh, no. What did I do? This is an f of x. I was like, what am I doing? That's an x right there. And that means that this is just plain x right here. which means that this is just plain x right here, as it's supposed to be. Okay. Crisis averted. Okay, I'm going to skip this. So I want to do one example, and we're going to use the general formula, the one that I failed to write down. So we're going to do a different log base with something inside of it. You pick up the prefactor of natural log, and then you have u prime over u. Okay. So consider pausing the video and giving this a try, and then resuming the video and then seeing whether we match. This part in here is what I'm thinking of as my inside function u of x. So h prime of x, I'm just going to use the formula. I'm going to have 1 over natural log of 4. Why 4? Because my base is b, which is 4. And then that's times, now I've got u prime over u, so 2x plus cosine of x over x squared plus sine of x. So that's 1 over natural log of b times u prime over u. Okie dokie. The next thing that I want to do with you is this. I'm treating it as optional for spring 2020. So if you're not into this, then by all means stop. But I'm hoping you're into it because this is a pretty cool method, and I think there is a web work problem on it. So we'll see how that goes. COVID-19. Okay, so the method of logarithmic differentiation, the purpose of it is taking derivatives of products and quotients of many things. And the reason that we want to do that is because take a look at this illustrating example down here. This example, if I try to do this problem without logarithmic differentiation, is going to be a pain because I'm going to have to use the quotient rule, and I'm going to have to use the product rule inside of the quotient rule, and there's going to be quite a lot of chain rule also. So if I try to do this example without using the method of logarithmic differentiation, it's kind of going to suck. We could get through it, but I don't really want to. So instead, what I'd like to do is work through this example to illustrate the method of logarithmic differentiation. And the first thing that I want to do with you is name the function, and let's call it, if it's not already taken, f of x on the left. So I'm going to write down that f of x is equal to x plus 1 squared times 2x squared minus 3 over, I'm going to rewrite this x squared plus 1 to the half. Okay, so that was that was step 1. Name it. Step 2, let's take the natural log of both sides. And on the left, we're going to leave it as the natural log of f of x, or whatever name it happens to be. So 2, let's take the natural log of both sides. So on the left, I'm going to have the natural log of f. That's equal to the natural log of x plus 1 squared times 2x squared minus 3 over x squared plus 1 to the half. Okay, so it doesn't look like I'm winning yet, but we're going to win. Because the next step that we're going to do is we're going to simplify the right-hand side, the log of the function, using these rules. So the log of the product is the sum of the logs. The log of the quotient is the difference of the logs. And the log of the power takes the power out front. So we're going to rewrite this. So we're going to rewrite this using the log rules. On the left-hand side, I'm still going to have the natural log of f. Fine. On the right-hand side, this is going to simplify as, let's see here, natural log of x plus 1 squared times 2x squared minus 3 minus the natural log of x squared plus 1 to the half. That was just one level of simplification. So that was just me doing this division turned into this right here. And now I'm going to take this multiplication and it's going to turn into a plus. And I'm going to take this 2 out front. I'm going to take this half out front. So I'm going to have 2 natural log of x plus 1 plus natural log of 2x squared minus 3 minus a half of the natural log of x squared plus 1. And that's as far as I can simplify it. The next thing we're going to do is we're going to take the derivative of both sides of that expression. On the left-hand side, okay, so let me write that down. 4. Take the derivative of both sides. So on the left-hand side, I'm going to have f prime over f. Because natural log of f prime is equal to f prime over f. Okie dokie. On the right-hand side, now we're going to take the derivative of each of these pieces. And the point is that this is really nice because no product rule and no quotient rule. Because they all turned into sums and differences. So this turns into, let's do the first piece. I get 2 times 1 over x plus 1. Let's do the second piece, the natural log of 2x squared minus 3, plus, let's see here, so 2x squared minus 3, and on the top, I'm going to have 4x. This is the derivative of the inside over the thing that was on the inside, minus a half of 2x over x squared plus 1. Okay, so we took the derivatives. Now the next thing that we're going to do is we're going to multiply both sides by f. Right? So essentially what we're doing is we're solving for this. And how we're going to do that is we're going to multiply the right-hand side. Well, we're going to multiply both sides by this f. So we'll get 5 multiply both sides by f. And I clear this to the denominator. So we get that f prime is equal to f, which was x plus 1 squared, times 2x squared minus 3 over the square root of x squared plus 1 times this whole expression here. 2 over x plus 1 plus 4x over 2x squared minus 3 minus, let's let those cancel, x over x squared plus 1. And now we could like do our best to like cancel, but things aren't it's canceling is usually like pretty difficult. I don't see any way to like make stuff cancel. We could like try to do like common denominator stuff with this. That sounds horrible to me. I don't want to do that. And so when I have 6 simplify as best you can, oftentimes it's like no. And so I'm going to call this step 6 simplify done. Okay. So this expression is the derivative that I saw, and I didn't have to do any quotient rule or product rule in order to get it. I think this is easier, particularly if the function that we're taking the derivative of had like other like more stuff on the back of it. Like if this product was bigger, then this would be really helpful, because I really don't want to do the product rule or quotient rule many times. So this is really helpful for complicated derivatives. Let's turn the page. I will simply say that on this page, I'm also, due to time constraints, I'm nerfing this content. And rather than spend time deriving any of these formulas or practicing working with them, I will simply touch on them briefly and say, here are the hyperbolic trig functions. And they follow a really similar pattern to the trig functions that are not hyperbolic. There's a cycle of length 2 here. So we've got no minus signs with sin and kosh going back and forth between each other. And then these are strongly analogous to the formulas for tangent, cotangent, secant, and cosecant. Some of the places that they differ in particular are some of these minus signs and the I missed an H. There's a typo. Sorry. I assure you the hyperbolic functions stay hyperbolic. That means there's probably another one missing somewhere too. Okay. So these are formulas, and you can use them just like you would any other derivative formula. Just like use the formula and then use the chain rule. They're rather formulaic. And then we've got formulas for the inverse hyperbolic functions as well. I have no idea what linverse is. Inverse functions. These are the hyperbolic trig. And they are what they are, with some notes on domain restrictions for them. I'll let you consume this yourself. They're formulas. They're domain restrictions. Yeah, I think that's all I want to say about that. Okay. Thank you very much for your time today. I really appreciate it. And I'll look forward to seeing you in class. For our discussion for questions and answers. Thank you so much. I'll talk to you later. Bye.